result is that the flux of this is the answer from all these surfaces added up, which I think the only other thing that we had that contributed to anything was what, 2 pi? So the final answer to this is 2 pi plus 8/3. That's the flux. All right, good? I have posted the videos for the homework all the way through 13.7. Those were posted as of this morning. So I believe if you look at I think I did 3 flux problems in class. I think I did 4 flux problems on video. I believe that covers 7 problems, and most of them are the homework problems. So I think I've done almost all the homework problems if you take what I've done in class and put it together with what I did online, or on video. And that does it, I believe, for this section, for what we're going to do. What I hope you've seen in these last examples is that, well, maybe if I look at the first example. We did flux on this right here. And when we did this one, we just used the hardcore formula of F dot the cross product of the partials. There was no way around it. There was no shortcut. And we just had to do it that way, and we ground out the answer. All right? That was the first example I did of flux. The next example I did, we realized that the surface could be written as a function of 2 variables, and so we used a special case. And then on the next example, which is what we did just now, we did a combination of a shortcut using the fact that paraboloid sideways could be looked at as a function of 2 variables, and then the very important fact that when you have a plane like this, a flat surface like this, that the normal is always the same, that you can kind of even take an even shorter shortcut to the answer. And then when we got to this last example, there was 3 super shortcuts, the front, the back, and the bottom, and then the top was the other shortcut. You know what I'm saying or not? Okay. Whenever you use the n in the problem, that's a very short way to the answer. But all of these could have been done with the original formula. But then you would have to find a parametric representation for each of these. And then you would have to take the partials and cross them. And it just can be tedious. But you can check it for yourself. It would work out the same. All right, that's it.
Will you be doing a review for the
Just study your homework. Just go over your homework and class notes. That's what I'm going to do when I make the final. I'm going to go through the homework. I'm just going to take a look at.
How many problems will you
I have to make it before I can tell you that. I can't tell you if I don't have it made. Okay, so on Stokes' theorem, I thought that we might start this. Before I even tell you what it is, Stokes' theorem, I thought we'd start with an example. And so that maybe you would come to appreciate it before I tell you what it is. Okay? So here we go. I'm going to go back. This is actually going back to line integrals. So recall line integrals. On vector fields. Do you remember that? And there was a formula for this. This was line integral, and then you were going to take f, you were going to plug in r of t, and then you were going to dot that with the derivative of r dt, and then this is going to give you, you're going to have some restrictions on t, which are going to be your limits of integration. So what we did was, when we had a line integral, and we had a vector field, what we did is we found a parametrization of C. So we found a way to draw the curve. We call that R of t. And then we evaluate the vector field at each of the points on the curve. We dot that with the derivative, right, which is like a tangent vector to the curve, and this somehow gave us our line integral, right? Yes? And then we also said, hey, if you put this here, then you mean that that curve is closed, right? And it's positively oriented. What is positive orientation? Which direction? Counterclockwise, something like that. Okay? So I would like us to start by doing this. I want us to find this. All right, find that for the following. I have a vector field of yz 2 times x times z, then e to the xy. And my curve C is the intersection of x squared plus y squared equals 16 and z equals 5. Yes, I strike my z's. So that's a 2. Yeah. I would recommend, if you don't strike your z's, to strike your z's. If you can't tell your 2's and z's apart, which I can't tell my 2's and z's apart if I don't strike them. Okay. Ready? Let's find a parametrization for this. Let's make sure you understand what this is. This is a cylinder, right? Infinite cylinder. Looks like this. Like that, right? Goes through the, runs out the z-axis. And then we have z equals 5, which is a plane. Z equals 5. Just slicing it. Right? Just cutting through and slice this somewhere, and you get that circle, right? That's our curve C. Positive orientation means that as I move along, right, as I move along counterclockwise, which is kind of weird to talk about that in three-dimensional space. Because what if you were looking from the bottom? Then is it still counterclockwise? It's not, is it? You understand what I'm saying? If I'm looking from the top down, it is counterclockwise. But if I'm looking from the bottom up, it looks clockwise, doesn't it? So that throws in some gray area, doesn't it? So what we do is, to get around that, is we say, if this is a closed curve, right? Positive orientation means that if you were to look at filling in between the curve, that as you walk along the curve, the filling, the inside of this is to your left as you walk around it. That's positive orientation. Does that make sense to you? That the surface between the curve, connecting this curve, will be to your left. All right, can you find a parametrization for C? What is that? I mean, that's a circle, right? Radius 4. And that's basically in the xy plane, right? But just moved up. So I could say like 4 cosine t, 4 sine t. And what about my z? It's 5, constant, right? That would draw it, wouldn't it? All right, let's go through. What are we going to need? The derivative, right? So we're going to need derivative of this. Oh yeah, t is between 0 and 2 pi. The derivative of this should also be pretty clean. Negative 4 sine t, 4 cosine t, and 0. What's next? take the vector field and plug in the curve into the vector field, and then dot that, not this into the vector field, then dot that with the derivative. So let's go ahead and find what f of r of t is. We'll write that down, and then we'll dot them in a second. F of r of t. I'm just gathering all the information together right now, okay? What is yz? Remember, we're working off of this one. Z is 5, right? Y is 4 sine t. So this is 20 sine t. All right. What is 2 times x times z? So 2 times x times z, 20, 40 cosine t. And then the last piece is e to the xy. E to the 16, right? Because this 16 cosine t sine t. That's f of r of t. And I'm supposed to take that and dot it with that, right? I need to dot those two together and then do my integral, and I should be there, right? Okay, so I'm ready to write this. The line integral over c of f dot dr is equal to the integral from 0 to 2 pi. All right, dot now. Dots are easy, right? This x component times this x component gives me negative 80 sine squared t. I like to see sine squareds. All right, now I do 4 cosine t times 40 cosine t plus 160 cosine squared t. I'm not happy to see the 160. 0 times, that's nice, right? The 0 times this, who cares? That really helped out quite a bit, didn't it? That 0 at the end there. And unfortunately, I cannot use Pythagorean, right? Although, I don't know, you have some choices here. Do you want to like replace your sine squareds with cosine squareds and put it all together, or you want to, what do you want to do? Split this into 2 now? The thing is, if this were negative 80, you could just factor out a negative 80 and then it would just be a 1 and great things would be great. That's not the case. No? I'll just choose this is what I'm going to do, okay? I'm going to say negative 80. Sine squared t is the same as 1 minus cosine squared t. Do you agree with that? And then plus 160 cosine squared t dt. I'm just trying to get it all in terms of cosine squared. I don't know why, I just felt like doing this. And now pass your negative 80 through. And what would you get next? Integral 0 to pi negative 80 plus what? 80 cosine squared t plus 160 cosine squared t, which is 240? 240 cosine squared t dt. Still good? All right, what do we do when we're trying to integrate cosine squared? Power reduce. So this is 0 to pi negative 80 plus 240, and then this right here becomes 1/2 plus 1/2 cosine 2t. That look familiar? You've done that a million times. Distribute the 240 through. So half of 240 is 120 and minus 80, 40? Okay, so we have 40, and then plus 120 cosine 2t dt. Can you all see that? right? All right, ready to integrate, finally. Antiderivative of 40 is 40t. And then here, antiderivative, you got to do some scaling. It's going to become like 60 sine 2t, and I'm evaluating 0, 2 pi. When you plug in 2 pi, you get 80t, or not 80t, 80 pi. And then when you plug in 2 pi here, you get 4 pi. Sine of 4 pi is 0, so that goes away. And then you plug in 0, you get zeroed out everywhere, and so your answer is just going to be 80 pi. Okay, so that didn't take us too long, did it? I mean, that was okay? That's kind of like a review of line integrals. So let's talk about Stokes' theorem. Stokes' theorem says the following. It's quite amazing, actually, what it says. I'm going to write it down for you first, and then I'll put it up here with the notes. It says that, let's say that you have a closed curve in three-dimensional space. All right, so you have this closed curve in three-dimensional space. Call it C, all right? And we're going to say positive orientation looks like this. Can you all kind of see that that's like a floating rubber band kind of in space? Well, if this C lies on the boundary of a surface, okay, so that black in there creates a surface, and that C is just the edge of that surface. So it's the boundary. And this is S. And it's oriented in such a way that, like I told you, if you're walking on the red curve, the surface is always to your left. Okay? Then we're going to have the following result. I'm going to tell you what it is in a second. Let me just show you a couple of examples of these that are a little bit easier to follow. What if I just, here's the x, y, z. What if I just draw a circle on the ground? Call that C. Then if I just look at the flat disk right there, does that curve C, or is that curve C the boundary of that flat disk? Yes, right? But I'd like for you to compare that to this. Same C on the ground, okay? But this time look at the upper hemisphere of a ball. Okay, so like you've got this ball up here, right? Do you see that? And if I look at that ball right there, that shell, then C is still the boundary, isn't it? So this surface in between here, S, I'll call it this one S1, and this surface here, S2, are totally different surfaces, right? But they have the same boundary curve. Understand? Here's the kind of mind-blowing Stokes' theorem. Stokes' theorem says that if you want this, if you want to know what this is, which is the line integral around this curve, then all you have to do is compute this surface integral. That's Stokes' theorem. And the reason why this is kind of mind-blowing is because it's saying that to do this line integral, we convert it to a surface integral where the surface S is any surface that has that as a boundary. Which means that if I use this surface or this surface, if I'm trying to find the line integral around C, I can use either one, I should get the same answer. So the surface in the center is totally independent of what's going to happen on that line integral. It's kind of crazy that it works that way. All right, so do I have these? I know I have it in the notes. Let's see how far away it is here. Okay, that was just me reminding you of what the line integral was. And then also I remind you how to do curl.